How's it going, everybody? We're going to talk about molar mass. So trace you through where that came from and how they calculate it. And so in order to do so, we need to talk about this guy, Amedeo Avogadro. He was an Italian lawyer and scientist, and he's credited with a lot of new discoveries and so about the time of 1811, he proposed the Avogadro's hypothesis. And so what is that? Equal volumes of all gases under same conditions of temperature and pressure contain the same number of molecules. And so I got a little cheesy picture here. And so we've got nitrogen, oxygen, and argon gas. And if you take a look, nitrogen is a diatomic molecule, which is made up of 2 nitrogen atoms apiece. Same with oxygen, but argon is only made up of just atoms. But he proposes that under the same conditions, all of them will take up the same volume. Doesn't matter if one is a diatomic molecule or not. And so that idea led us to other information, which is the AMU. So the AMU, as you recall, is a unit that we use to measure the mass of an atom. And so 1/12 the mass of a carbon-12 isotope is how they established that measurement. And so a couple examples there: hydrogen has the mass of 1 AMU and carbon 12 AMUs. And so we can calculate the entire molecular mass of any molecule, any substance, just by taking their masses, their atomic masses, and adding them all together. And so see the example down below of H2SO4, of 2 hydrogen atoms with roughly a mass of 1, right there. Sulfur with the mass of 32.07, and we have 1 sulfur atom, and then 4 oxygen atoms with a mass of 16. So you add those all together, and so 1 molecule of sulfuric acid will have a mass of 98.09 AMUs. And so this is useful information, but it becomes even more useful when talking about molar mass. So both of these things led us to what we call Avogadro's number. And so it's written right there on the screen there. N, Avogadro's number, is equal to 6.022 times 10 to the 23rd. 6.022 times 10 to the 23rd, what, you may ask? Well, 6.022 times 10 to the 23rd, anything. And so they refer to that as a mole. A mole of anything is 6.022 times 10 to the 23rd of that substance. And so show you some examples here. So it's again 6.022 times 10 to the 23rd. You could have a mole of carbon atoms. That would be 6.022 times 10 to the 23rd atoms. A mole of copper atoms, 6.022 times 10 to the 23rd copper atoms. A mole of oxygen molecules, 6.022 times 10 to the 23rd molecules. A mole of formula units of sodium chloride is 6.022 times 10 to the 23rd. A mole of, once again, the H2SO4 that we just looked at, 6.022 times 10 to the 23rd of that molecule. And then the bottom one there is glucose. So a mole of glucose, 6.022 times 10 to the 23rd molecules of glucose. So it's a number just like we use for things like a dozen donuts. So it's a word that represents a number. So a mole is just like any of these words here that we use to represent numbers. So a dozen, we know, is 12. We're used to saying a dozen donuts, or a pair of socks, or a pair of pants refers to 2. A couple of the other ones that you might not be aware of would be a ream of paper. So a ream is 500. A gross. Gross is a word that represents a number, which is 12 dozens or 144. And so it's exactly the same thing. I know it's kind of hard to wrap your brain around, but a mole of anything is specifically that number. The number just tends to be, well, the number just happens to be a very large number, 6.022 times 10 to the 23rd. So just to give you an idea how large a mole is, so if you had 6.022 times 10 to the 23rd marbles, it would cover the surface of the Earth to a depth of 6 miles. And so it's a very, very large number. And so 6.022 with another 20 zeros after it. And so it's a massive, massive number. And it has to be because atoms and molecules are very, very small. Why is this useful? And how do scientists measure this number? Well, I got a picture here of various different substances. A mole of all these different substances, so mercury 2 oxide, sucrose, sulfur, some copper, some just table salt there, sodium chloride. All of those are moles. And so do you think scientists, they sit there and count out 6.022 times 10 to the 23rd of any of those substances? That would be ridiculous. It would be a massive number, and it would take multiple lifetimes to count that. And so how do scientists actually measure out a mole? And, well, here comes the magic. So we just talked about AMUs and how to calculate AMUs. You take the atomic mass of any atom and what atoms are included in any substance, and just add those together, and you get the atomic mass or atomic weight of that substance in AMU. So here we have a picture showing water molecules. And so one molecule of H2O is 18 AMUs because we have one oxygen, which is 16, and two hydrogens, which are 1 AMU apiece. Add them together, you get AMUs. And so if you count out Avogadro's number, or a mole of water molecules, you get 18 grams. You take the AMUs of any substance, just change the units to grams, and you now have a mole of that substance. Let's show you another example. So just a single calcium atom. So 1 mole of this substance will be, well, 1 atom of calcium would be 40.078 AMUs. And so very, very small mass. But if you wanted a mole of calcium, all you have to do is take that atomic mass and change it to grams. So now 40.078 grams of calcium would be a single mole of calcium. So much easier to measure than 6.022 times 10 to the 23rd calcium atoms. So one more example here, H2SO4, the one we talked about before. So you saw the calculation. So 2 hydrogen atoms. You have 2 times the atomic mass, 1.01, gives you 2.2 or 2.02. 1 atom of sulfur would be 30.2.07, and then 4 atoms of oxygen, 16.00. So you get your masses there, and I'm already showing that. So I'm already showing that if you just change the AMUs to grams, add them all together, you have 1 mole of sulfuric acid. So once again, much easier than calculating 6.022 times 10 to the 23rd molecules of sulfuric acid. Now we just have to get a scale, measure out 98.09 grams of that substance, and we now have 1 mole. I hope that helps. It's always good to practice, and so practicing a few different substances will help you remember this, and so I highly suggest that you do.